University of Auckland. Chris, who normally runs these sessions, is away enjoying himself on a cruise ship, so we haven't got him here tonight. Just quickly before we start, has anyone got anything to say in terms of announcements? We've got only 2 more meetings left this year, so we've got the monthly meeting next week, and then the last meeting of the year will be in the planetarium, reviewing the sun, light, sky. And then we don't have, for those who don't know, we don't have meetings in January, so we start again on the first Monday of February. So welcome, Sohan, thanks very much for coming along, and really interesting topic, black holes and dark energy. So thank you.
Thank you. Thank you very much for coming, given that the weather was not very good, and sorry for the technical difficulties. So I'd like to thank the society members for giving me this chance to present here. So as you can see, I'm going to talk about black holes and dark energy. So in particular, this talk would be about a recent paper that came out, I think this year at the end of February. And then we also did some work on it at Auckland. So I'm going to discuss that paper and also the work that we did in response to that paper. So this paper that came out in February became very popular. It grabbed quite a lot of headlines. So here are some snapshots that I've got. So they suggest that black holes might be the source of dark energy. So I'll explain what dark energy and black holes are and how they are related to each other according to them. But here are some headlines. Dark energy could be created inside black holes, scientists claim. The other paper says black holes are accelerating the expansion of the universe, says cosmologists. And there's another headline, dark energy from supermassive black holes. And you can see that there's not full consensus on the idea. Physicists spar over the radical idea. So the aim of the talk is to discuss the recent work that attempts to provide an explanation for the source of dark energy. We will also discuss some of the relevant history in order to build the concept. And then since any hypotheses should be tested before it is accepted, so in the second half of this talk, we will discuss some of the observational implications of their result. So why do we need dark energy? So up till 1920, it was believed that the universe is static. In other words, it does not change, and it is like eternal, unchanging thing on large scales. But in 1920s, Hubble discovered that the universe is not actually static. So he looked at stars which are distant from the Earth. So he saw that those stars were moving away from Earth, and so the relation that he derived was something like this: the straight line that we have at the center called there's the pointer. So so on the y-axis, for example, I have the speed of the different stars that you can observe, and on the x-axis I had their distance. So Hubble discovered a relation which is the straight line, 45-degree straight line. So from here, Hubble concluded that the stars that we look at are moving away from us. So and because they are at a distance, and the further away we look, the more away they are moving from us, that means that things are not static on a large scale. Instead, the universe seems to be expanding wherever we look from the Earth. So, so if things are going away from us, then because they are attracted to each other gravitationally, you will assume that one day those will slow down because of their mutual gravitational attraction and then fall back in. So something like the explosion that I showed down there. So let's say we have a planet that for some reason explodes, and the fragments go away, so they move away from each other, and eventually they fall back into the origin because of their mutual gravitational attraction. So that was the idea, that maybe the universe is not static, okay, it's expanding, but one day it will reach its maximum possible size and then again start falling back in. But in the 1990s, we observed that the universe is not just expanding, but it's expanding at an accelerated rate. So the current trend is that accelerated curve that I show there. So that's the observation, that's the evidence that we have from recent observations. So the reason why Hubble was not able to deduce this trend is because his data was only in this region. So now we are able to see much further away, and so the conclusion that we get is the universe is accelerating. So that's a very puzzling problem, Because a deaccelerating universe makes sense because gravity would attract things, and so the speed would deaccelerate and eventually they would collapse. But what can be causing an accelerated expansion? So people had no clue, so they came up with this mysterious name called dark energy. Dark because we cannot really see the source of this energy which is causing this accelerated expansion, but at the same time it seems to be there. So therefore the name dark energy. No, it doesn't seem to work. Cool. So both black holes and dark energy were introduced by general relativity. So general relativity came around 1916, and both these ideas were consequently developed by the theory. So initially, both black holes and dark energy were not believed to exist. So dark energy, even though was first time discovered in the 1990s, the idea was introduced in 1916 itself by Albert Einstein, as I will discuss. So initially, it was believed that both of them might not exist. Let's go through a brief history. First, we'll discuss what really dark energy is, or at least what are the different ideas surrounding dark energy, and then we will turn towards black holes. Eventually, I'll discuss a little bit about gravitational waves. The reason being is that we are going to focus on black holes, and because we cannot directly see black holes because they are black, so we have to see them using some other mechanism, which turns out to be gravitational radiation. So I'll discuss a little bit about gravitational radiation as well. Next slide, please. So currently, dark energy constitutes roughly 68% of the mass energy budget of the universe. So as we know, mass and energy are sort of equivalent, or we can put them on an equal footing. So if we convert all the matter, regular matter in the universe, then we see that it only constitutes roughly 5% of all the mass energy present in the universe. The rest, 27% right now, is dark matter, and 68% is dark energy. But that has not always been the case. It's just the present day energy density budget of the universe. In particular, in the past, so if we look at this diagram, here is the Big Bang. So this axis shows the time evolution of the universe. So here is the time equals 0, and then we are currently somewhere here. And this is the expansion of the universe. So at this point, dark energy was... it works now.
It's working.
The thing's working, is it? Yeah, it's working. Cool. So over this point, dark energy was not dominant, so its effect cannot be seen. But if you look at this curve suddenly changed the shape over this region, and it suddenly goes from like that to like that. So this is the point where dark energy first became a dominant feature in the evolution of the universe. And right now we are somewhere here, and it constitutes 68%. It will constitute more of the energy budget of the universe in the future, and it constitutes less in the past. So dark energy has got these different names in the literature. It goes by 3 different names. One is the cosmological constant, the other is the vacuum energy, and the last bit is the dark energy. So why do we have 3 different names for the same thing? So cosmological constant was introduced by Einstein himself in 1916. So as we know, general relativity is a theory of space-time. So the question of biggest scope that one can ask from this theory is, what is the structure of the entire universe? So Einstein himself tried to do this. So here I have written the Einstein equations. So these are the core part of the prediction of relativity. These are 16 different equations written in a very compact form so that it looks only one equation, and that also has just symbols in it. So those symbols have associated meaning with them. So on the left hand side, for example, the left hand side controls the curvature of space and time. On the right hand side, the 8 pi g is a constant factor, so it's not important. The t bit is the mass energy that we have within a domain of interest. So the right hand side is the mass energy. The left hand side is the curvature of space-time. So one way of saying this is the mass energy decides the curvature of space-time, and the curvature of space-time then decides the dynamics of the mass energy. So what Einstein, so those were the original equations that he came up with. But as I was just telling you, Einstein thought that the universe is static, so it's unchanging. But gravity is an attractive force, and therefore the universe should not be static on large scale. It should collapse eventually. So in order to keep the universe static, what Einstein did is added this extra term called lambda, which was called cosmological constant. So he added this term to the left-hand side of this equation in order to make the universe static. And so, as you can see, this has an effect of creating a repulsive behavior because it counteracts the influence of gravity. So that was Einstein's contribution. But later on, as I mentioned, Hubble discovered that the universe is not static. So then Einstein said he has made a very big mistake. This is the biggest blunder of his life. He should not have ever introduced such a constant. His original equations were already very good. So that was the first impression of somebody introducing an additional bit into the equation artificially to explain the observed phenomena around us. Now, another name is just the dark energy, which is a modern name. So after discovering the accelerated expansion in the 1990s, people thought of no better idea but to reintroduce the same constant that Einstein had in the equation. And so they said, okay, we have this constant again that is now somehow causing the accelerated expansion. So it's again a cosmological constant, the same equation. But then what if we shift that constant to the other side of the equation, which is done down here? So we bring that lambda bit here, and then we give it a new name called rho. And that's because we remove some constant factors from that lambda. And now this bit, because it's on the right-hand side, and if you remember, right-hand side is the energy density in the universe. The left-hand side was the curvature. So now this bit is called dark energy because it's on the energy density side of the Einstein equations. So in modern language, this bit is called dark energy, which we have introduced into Einstein's equation to make the universe expand at an accelerated rate. So there's another name for dark energy, which is called vacuum energy, and this is the last one. So far, we have not given an explanation as to what might be causing this mysterious dark energy or what might be the source of the cosmological constant. At the same time in 1990s, people came up with explanation for the source of the mysterious dark energy. So that came from quantum mechanics. So we know that in quantum mechanics, things do not have zero energy. So even if we cool down stuff to absolute zero, it still has some energy left in it. Now, in quantum mechanics, or at least in quantum field theory, different objects are thought to be quantas of an underlying field called quantum field. And these fields, they lie everywhere within space, and they constitute, even at their absolute minimum, they have some energy in them, which is called zero-point energy. So here's like a rough diagram where we have empty space, and these are quantum fluctuations which carry energy in them. So people thought that maybe because these quantum fields exist everywhere and they have this zero-point energy, this zero-point energy might be the source of dark energy. So Steven Weinberg calculated the value of this zero-point energy of the quantum fields. And the answer he got was 10 to the power 120 times larger than what is required to mimic the influence of dark energy that we see on the universe today. So this prediction was deemed the worst prediction in physics, although it's a very, very nice idea because it solves the problem of dark energy without reintroducing something new. But it's off by factors of magnitude, orders of magnitude. So we got these three names, but we still don't have a proper explanation. And that was the story so far. So this paper now gives another explanation. So they use black holes. So let me quickly discuss a little history of black holes. So black holes were also predicted by general relativity, which I call GR there. So they were predicted by general relativity in the same year, 1916, by Carl Schwarzschild. So Carl Schwarzschild showed that this black hole is a solution of the Einstein equations. And so initially, people were very skeptical about the existence of anything like a black hole. The reason is quite simple. If you look at this diagram, you'll see that it's a star. So the star is supported by the nuclear fusion that is happening in the core. So gravity wants to compress the star to a tiny point, but the nuclear fusion holds it to a stable configuration. But what happens once the star does not have any nuclear fusion going on in the core? So eventually, the star runs out of its fuel and stops fusing, and then gravity there is nothing to counteract the effect of gravity, and it keeps on compressing. But you might imagine that at some point the electrostatic forces between the matter would then act as a source of repulsion for the gravitational contraction. So it will the electrostatic repulsion would eventually counteract the gravitational attraction. So that was the idea, but then eventually in the 1920s, quantum mechanics was a new thing at that time, and people applied. So if we want to study something that is very compressed and constitutes particles, we would like to study them from a quantum mechanical perspective. And it turned out that if you use quantum mechanics, then you will find that a star cannot be supported by this electrostatic pressure. Instead, what we require is something called a quantum mechanical degeneracy pressure. So it's a quantum mechanical effect, but even that thing cannot support stars indefinitely. So that's the radius of a star, and this is its mass. So a star of mass, let's say 1 solar mass, can be supported. So it will not collapse into a black hole. It will remain like a stable thing. But if the mass reaches a certain threshold limit, beyond that the radius goes to 0. So if the mass happens to be larger than this 1.4 solar masses roughly, then the system would not be able to withhold its own gravitational pull, and eventually it will be reduced to a radius of 0. So this was a good piece of evidence against the or supporting the idea that black holes could exist in reality, because there's nothing that counteracts gravity eventually. So for some time people did not agree with the finding of this result, later on, later on people also. So first of all, this was supported by electron degeneracy pressure. So what happens is that electrons would eventually get captured by the protons, and we will form neutrons. That's again a phenomena from particle physics. So if you take electrons and form neutrons out of that, you will eventually not reach this configuration, but before even reaching this configuration, we will reach a configuration that is called a neutron star. So you will have a tightly bound star, which is now made of mostly of neutrons. So then the idea was that maybe we do not have this white dwarfs, as they are called, but instead we will end up with neutron stars. But then the idea again remains that if you put sufficient mass, the neutron star would also reach a radius of 0. Or at least it would be compressed so much that it reaches within its own event horizon, and we form eventually a black hole. So this idea was introduced in 1920s and 30s, but people still were skeptical about it because of other reasons, and eventually it was in late 1960s or early 1960s that people developed a consensus that a thing like black hole might really exist. But we first found observational evidence for black holes in the 1960s, which came in the form of Cygnus X1. So Cygnus X1 is a binary system. I've got an artistic impression on the top figure. Here we have a star on the left-hand side, and on the right-hand side we have a black hole. So the black hole is feeding on the mass of the star, and it generates a lot of X-ray radiations. So observers saw X-ray radiation coming out from somewhere, which was not really anything, like apart from some accretion disk that we see, we do not see anything at the center. So this was something that was believed to be a property of a compact object like a black hole. So that was the first evidence. But the most conclusive evidence came in 2015 when LIGO discovered the gravitational wave radiation. So this is the picture. So LIGO discovered the merger of two black holes by observing the gravitational wave radiation that that these two systems emit. And then again in 2019, the Event Horizon Telescope, or EHT, took that picture of the black hole, which is on the left-hand side. So that's a very blurred out version. A real picture would look something like that. So now we have a lot of evidence that these compact black objects do exist in nature. So far I have told you that people did not agree initially on the existence of black hole. Now we got evidence, but what really are black hole? So unfortunately, I cannot tell you what they are, but I can tell you what they are not. So John Mitchell and Laplace were the first two people to propose the idea of something like a black hole. They did not call it a black hole, they call it a dark star or a black star. So the idea was that if we put sufficient mass, if we put sufficient mass into a tiny region of space, then eventually the gravitational pull would become so strong on its surface that even light would not be able to escape to infinity from that surface. So if you are very far away, you would not be able to see that thing, because even light cannot escape from the surface to your location. So that was the idea behind dark star. Now, black holes in general relativity have very similar property in the sense that light cannot escape, but there's a difference between that dark star and the black holes of today. For those dark stars, light cannot escape to infinity, but it can escape to a finite distance and then eventually fall back. For the case of black hole, it cannot even escape an infinitesimal distance away from the horizon. So horizon is like a surface from where nothing can leave at all. And then there are other peculiar behaviors of black hole, like they have very different physics close to their horizon and other. So here I have for example, a diagram. So I show so it's like a two-dimensional cross-section. So here we have the sun, and the additional structure on the side represents space. So we have the sun, and the sun has mass, so it creates curvature. Now, when the sun becomes a white dwarf, so when it ends its nuclear fusion and it's no longer able to support its gravitational against its gravitational pressure, it will compress to a tiny region. So there we have the white dwarf, and had the sun been more massive, it would have collapsed into something called a black hole. So here we see that there's no matter here anymore. So it's like an empty region of space, and the technical way of saying that is the matter has fallen into the singularity, which really don't mean much. So black holes are just saying vacuum solutions of Einstein's equation. So there's nothing really within the event horizon of the black hole in relativity. So in that sense, they are very different from black stars because they do not have a surface. You can just fall through their event horizon, whereas those black stars have a rigid surface that you would go and hit. So, so hopefully this was a little bit of introduction to black holes. So how are these black holes and dark energy, which seem very different concepts, how are they connected? So from the recent publication, it's hard to say how exactly they are connected. They do not make it very clear, but they hypothesize that, so their hypothesis is over here, point number one. They say that compact objects, for example, like black holes, are not really black holes, but they are instead something very different, which on the outside looks similar to black holes. So they call them, or in the literature, such objects are called gravastars, which stands for gravitational vacuum condensate star. So it's an acronym, and it's called, and then these gravastars are able to interact with the outside space and create this effect of accelerated expansion of the universe. So what are gravastars in more detail? So as I've just said, black holes are strange objects in the sense that they have these event horizons from where even light cannot escape. And then there's another problem with black holes, which is that they have this singularity at their center, which is the point where equations of relativity break down. So we do not know how to mathematically deal with those, or that particular point at least. So that's a problem in the equation, the existence of a singularity. And then there's another paradox associated with black holes, which is called an information paradox. So I won't go into detail regarding what the paradox is, but it's a disagreement between the prediction of quantum theory and general relativity. So black holes has got these two problems: existence of a singularity and information paradox. On the other hand, gravastars are objects that do not have those problems, but at the same time they make the same prediction that black holes do on their outside. So a black hole would, a gravastar would also look black, but in contrast to the black holes which have an event horizon, these gravastars will have a firm surface. So if you go, you will hit the surface of the gravastar, so you won't go past the event horizon. However, you might ask, how are these things being supported? Because didn't we just see that the neutron stars and the white dwarfs cannot be supported if you compress them sufficiently enough? So the claim is that these gravastars have in their interiors vacuum energy or dark energy, something that we do not understand, but because dark energy has this negative pressure, it repels everything. The claim is that if you put vacuum energy into the interior of these gravastars, then they would prevent further collapse of this system. And therefore, if you put sufficient vacuum energy such that this gravastar just goes and kisses the event horizon but does not go past it, then you will be able to maintain a stable configuration of that mass, which does not at the same time goes past the event horizon. So a gravastar has a surface that you would notice, no event horizon. It also looks black because it's very compact and would have nearly all the properties of the black hole. It would not have a singularity for the reason that we do not have a black hole, but like a star, but very compact star. And these things were predicted a long time ago, but they have been popular since 1999, I guess. They were predicted in 1999, so not by these authors, but by somebody else. But they make use of it. So, so point number 3. So they hypothesized that the black holes, or in other words, the gravastars, if their masses grow in proportion, or at least they say that their masses should grow in proportion to the volume of the universe. So if their masses grow over time, then because their center contain these dark energy or vacuum energy, that vacuum energy will also grow in proportion to the volume of the universe. And because now we have vacuum energy which is growing over time, but now restricted to the center of these black holes, this vacuum energy will cause a negative pressure on the rest of the universe. So it will then recreate the effect of the accelerated expansion of the universe, but now we do not have dark energy lying everywhere, but we have concentrated it to the center of these gravastars. And so the negative pressure results in the effect that we attribute to dark energy. And then the crucial point in their paper is that they show observational evidence to support their claim. In other words, they show observational evidence that the mass of the black holes grow over time. So they look at some distant galaxies, and they say these galaxies are elliptical galaxies. In other words, they're old galaxies, so they do not have much matter flying around. Most of the matter has either gone into stars or have gone into compact remnants. So they look at this supermassive black hole residing at the center of these galaxies, and they see that the mass of the black hole grows over time. So for example, if I look at a black hole which is very much into the past, so I look very far away, and then I look at some black hole which is nearly which is closer to the Earth, I see that the one that is closer to us is much more massive than the one that those are far away. And the good thing is that they predict a trend which they showcase in their observations. So they show exactly that as the universe becomes older, the mass of the black holes grows in proportion to its volume. So they make a hypothesis and they show the evidence for this. And that's why the paper got a lot of publicity. So they have restricted dark energy to the center of these compact objects whose masses are growing with time, and therefore they claim that this is the reason why the universe is expanding. So this is a nice proposal in the sense that not only does it solve the problem of dark energy, because now the dark energy is restricted to the center of these compact objects, but it also makes the black hole regular. In other words, it makes them singularity free and prevents certain bad things that come with the black holes in relativity. But can we test this hypothesis? So they already provide one observational evidence, but can we test it? Can we see what it means for the rest of the physics? And it turns out we can, and we'll look at one or at least a few cases in the rest of this talk. So I'll show you some observational implications of their claim, assuming that their claim is true. So as I mentioned earlier, we will be using gravitational waves to test this claim, so because that's the only way we can look at black holes, apart from the systems that have accretion disks around them, so they become electromagnetically visible. But if we just have a black hole, we cannot see it, so we require these gravitational radiation. So, one slide introduction to gravitational waves. So gravitational waves are ripples in space-time, so they propagate through space-time just like electromagnetic radiation does. But they were indirectly detected in 1960s using something called a Halsey-Taylor pulsar. So it's a pulsar system which people saw. So pulsars emit these pulses from their poles, and these pulses, when they reach Earth, it's like a lighthouse effect. So we see the pulse, then we don't see it, then we again see it. So they come at some precise frequencies. So if the system radiates gravitational radiation, the orbit of the pulsar will decay over time because the orbital energy is being transferred into this gravitational energy. It's a gravitational wave energy. So we will detect a change in the pulsar time period. And so that is what people did, and so the theoretical prediction matched very well the observations. And so we had some evidence regarding the existence of gravitational waves since 1960s. But the direct detection was made in 2015 by the LIGO detector in the US. So gravitational waves in principle are easy to produce. For example, if I rotate my hand like this, I'm producing gravitational waves right now. But the problem is that these gravitational radiations are very weak. If we really want to detect a gravitational radiation, then what we need is the merger of two black holes. For example, on the top image, I show two black holes that are right above to merge. And when they merge, they emit gravitational radiation of very high intensity. And this is the sort of intensity that we require right now for them to be successfully detected. So what effect would a gravitational radiation or a gravitational wave have if it passes through the Earth? So in the bottom diagram, if we have a circular ring, for example, and the gravitational radiation or the gravitational wave passes right through the plane of this figure, then the circular ring would behave like that. It would one time extend in this direction and then squish and then extend in that direction. So we see that it causes a change in length of the ring. It causes a change in the diameter of the ring. And this is the exact idea that LIGO uses to detect such gravitational waves. So say, for example, we have this detector here, the L-shaped detector, and a gravitational radiation passed by. So it goes out of the page, and this detector is into the page. Then it will do the exact same thing to the arms of the detector. One arm would shrink, the other arm would extend. So this is highly magnified effect. It would be very, very tiny effect, but that would manifest. The same thing would manifest for the detector as well. Now, if we throw light into the arms of the detector, and assuming that the detectors were equal length initially, then the light in this arm might travel less distance compared to the light in that arm, or it could be the other way around. But eventually, they would not be traveling same distances. So when we combine those two light beams on this end, we will see an interference effect. Because the light beams have now traveled different distances, so they might interfere either constructively or destructively. So we'll see a fringe pattern. And that would then tell us that a gravitational wave has passed by. So that's how we detect these mergers. So here's the diagram. So initially the black holes are far away. They are inspiraling each other. So here we put some accretion disk around the black hole so that we can see them. But they inspiral and then they come and merge. And this is the final phase. So this is the frequency, the behavior of the wave. So the y-axis is the amplitude of the wave, and the x-axis is the frequency. So we see the frequency goes up as they come together. Also, the amplitude goes up near the merger phase. And this is the high amplitude region which we detect, because high amplitude means high intensity, and high intensity means better chance of detection. So gravitational radiation produced by the merger of binary black holes, and that's how we can see the black holes. And this is what we're going to use in the next bit to test their prediction. So this is the paper that we wrote in response to their paper, where we looked at the observational implication of cosmologically coupled black hole, or as they call them cosmologically coupled because they are coupled to the cosmic expansion. So we made three separate predictions. So the first thing is that as I've just mentioned, these binary black holes merge over time because they emit gravitational radiation. Now, in our universe, almost all black holes or all binary black holes that we have would not merge because gravitational radiation is not very efficient in removing energy from the binary system. So why is that? That is because the gravitational radiation, the time scale of the rate at which the gravitational radiation removes energy from a system is inversely proportional to the r to the 4, where r is the separation between the binary. So it's very weak. So for example, if we have two 30 solar mass black holes, so two black holes each being 30 times the mass of the sun, then this system would merge within the age of the universe, which is close to 14 gigayears, if their initial separation is close to 50 solar radii. So this is a very tight configuration. If you put black holes at a further distance, they would not merge within the age of the universe. So for example, here, I showed the same thing, but now for many systems. So here I have the initial period of the black holes, and here I have their total masses, assuming that both of the black holes are equal massed. So if we just focus on this solid curve, then this curve shows the black holes that will merge in 10 to the 15 years. So this is roughly 10 to the 5, so 100,000 times. This time period is 100,000 times larger than the age of the universe. So we see that if the masses of the black hole, let's say their total mass is 50, then only the black holes which have initial period around 100, 200, 300, roughly around 300 days would be able to merge. The others would not merge. And so if we really want to merge black holes which have a period of 1,000 days, we have to go further up. And so this is already much larger than the age of the universe. So black holes do not really efficiently merge using gravitational radiation. But what if their masses go up with time? Because if we are making black holes more massive, that means we're raising their mass. And as we just saw in this diagram, more massive black holes are able to merge more efficiently. So the less massive one, only small period ones would merge, but more massive, we can go to larger periods and even those merge. So in this diagram, for example, I show the merger time of black holes if they were just ordinary black holes, so no dark energy interiors. And here I show the merger times of the same black holes if they have dark energy interiors. So let's focus on this red curve. So the red curve represents a black hole, a binary black hole system that was produced at somewhere around redshift 1. So redshift 1 would be roughly when the universe was 7.5 billion years old. So a black hole that was produced 7 billion years ago, if its mass does not go up, if the mass of the binary doesn't go up, then it would merge. You can see, let's choose a number. Let's say it merges in 10 to the 15 years. Then for the same binary, if its mass goes up, then it will merge way sooner. It will merge before 1 billion year. So the merger times have now been accelerated rapidly because the masses of the black holes are going up in their hypotheses. So because the black holes are merging much more faster, that means we should detect much more mergers in our gravitational detectors that we've got. So we would like to see how many mergers would we expect to see on Earth if their hypothesis is really to hold. So for example, here I show the masses of the total masses of the black holes, and here is the number of detections that we would make every year. So this histogram, the gray histogram, is the detected data. So these are the detected numbers in the third observation run of LIGO, which was, I think, 2019, 2020, so before COVID. So they detected roughly 90 binary black hole mergers in that 1 year time period, 80 to 90. Now, if black holes are really sources of dark energy, then we find that the mergers should go up by orders of magnitude. So we should be seeing like 4,000 or 5,000 mergers every year, which is much more than what LIGO has already detected. And not only would the mergers go up, but the masses of the systems would also grow up. So the most massive system that we have seen has been roughly around 200 solar mass, so the combined mass of the system. But now here we see that the masses should be very, very large, which we do not see. So this is a counter evidence to their claims. Their claim does not support the recent observations. So that was one bit. Another bit is looking at the spin of these black holes. So because the black holes that they looked at were supermassive black holes at the center of galaxies, they claim that these black holes grow in mass over time. But at the same time, their angular momentum remains conserved because they say that they are not accreting mass from anywhere. Their mass is going up because they are coupled to cosmic expansion. So if their angular momentum remains conserved, but their mass goes up over time, that means they would slowly spin down, right? They will slowly spin down and their spin would fall. So we look at, so we calculate that assuming that the spin of these black holes does remain conserved, what would be the spin of a black hole today, given that it was born some time ago in the past? So we find that all black holes should slow down to nearly zero rotation. So there's a parameter that people use to measure the spin of black hole that I've called that one, that thing A there. So the maximum value that A can have is 1. So 1 means the black hole is rotating maximally, so at the maximum possible rotation, whereas 0 would mean that the black hole is not rotating at all. So we find that if we wait for 6 gigayears, then any black hole, no matter how fast you produced it, how rapidly rotating you produced it, would spin down to nearly 0 within 6 gigayears. So if the black holes at the center of the galaxy that they looked at are really coupled to cosmic expansion and their mass is going up, they should spin down. But this is the data that I got for the same black holes that they looked at. And so here is their spin that people have inferred from observations. And their spin does not seem to be close to 0. They are rotating quite fast, like 0.8, 0.9 is very fast. The black hole at the center of our galaxy is rotating close to 0.6. So, the black hole at the center of our galaxy is also accreting mass and therefore gaining angular momentum continuously. So these are rapidly rotating systems, again not supported by the claim that they make. And the final bit is we looked at something called primordial black holes. So primordial black holes are black holes that would have been produced when the universe was very young. So it was very young, very dense, and if in this dense universe, if there is a tiny pocket of overdensity, then that pocket might collapse and form a black hole very quickly. And because the early universe was very dense, because of tiny quantum fluctuations, it's relatively easy to produce such high density pockets. So if a black hole is really produced in the early universe, then any black hole that has mass larger than 10 to the 15 grams should be stable in the sense that it would not evaporate over the age of the universe. So as we know, black holes should evaporate because they emit something called Hawking radiation. So this is the horizon of the black hole, and it emits two particles. One goes in, one goes out. And so the outgoing particle is the one that takes away the mass energy of the black hole. And if we wait for a long enough time, we will see that the entire black hole would have evaporated. So, but if a black hole produced in the early universe has a mass larger than 10 to the 15 grams, it should survive till today. That is something that we can calculate. So, assuming that a black hole is produced in the early universe with mass 10 to the 15 gram, we find that that black hole today should grow to a mass of roughly 10 to the 11 solar masses, which is much more massive than what we see, much more massive than the black holes that we see at the center of the galaxies. So the primordial black holes, if formed in the early universe, should be much more massive than the black holes at the center of the galaxies, and we should have discovered some at least, although we're not sure if primordial black holes were really produced. And so this prediction is not really something that could negate their claim, but at the same time, it shows the implication of their claim. And we have not found any such system. So again, not a positive result for their prediction. So those were the three predictions that we made, which does not support their claim. I think that was my last slide. So to quickly summarize, so we discussed three sources of dark energy: cosmological constant, vacuum energy, and dark energy. All of them refer to the same thing, but maybe different mechanisms of generating them. Then we discussed a black hole mimicker, which is called gravastar. So from outside, they very much look like black holes, but they have solid surface, so no event horizon, and their interior is filled with dark energy, which supports them against collapse. And then we looked at a recent hypothesis, which suggested that these black holes, which are sort of like gravastars, could be the source of dark energy because they have the interiors filled with it, and their masses should grow over time to reproduce the effect of present-day dark energy, the present-day accelerated expansion of the universe. And then we looked at the observational implication of that claim, and we found that current observations do not support the idea unless and until there is some major modification to the already known physics, which is again a challenge because you're proposing something new and then making more changes to the already known physics to fit that piece of hypotheses. Thank you for listening.
Questions?
Sure.
The energy interference from the merging of the black holes, how quickly do they travel?
They travel at the speed of light.
Speed of light, okay. And what about ones that are travelling away, accelerating, they become faster than the speed of light, do they?
So they do exactly what the light does. So
They may never reach us.
yes. So if the gravitational radiation from the region which is now beyond our observable horizon would not reach us, yeah.
So, and if we look at those LIGO results, there seems to be very few that they're detecting, like one a year or something.
These ones?
Yeah, is that mostly what they're detecting, neutron stars?
So that's for this entire thing is for 1 year, and what I've done is, so it might look quite less because I've distributed that from 0 to 200. Yeah, but these are actually roughly 90 observations that they have made between, so the masses are somewhere between 3 to, or maybe 5 to 200, it's the masses of the binary, and roughly 90 observations that they've made. This blue curve is the one that we get if there is no new physics, so the black holes are ordinary black holes, so we underpredict, because these systems might be coming from many different pathways. We only look at one, which is two black holes born from stars, eventually merging. And then using this same thing, if we then make those black holes as the source of dark energy, as they suggest, then these ones go up by order of magnitude.
On the mirror arrays that you showed on the other graph, when you get the interference from the black holes merging, is it actually making the mirror slightly further away, or is it affecting the speed of the light between the two?
It's making the mirrors go away, or maybe squish a little bit, but that effect is very tiny, so we would not be able to detect that. What we instead do is we detect the interference pattern of the light. So if we find a change in the interference pattern, that means something has moved one mirror with respect to the other. And assuming that that thing did not happen because of some sort of seismic noise, so we have isolated all forms of noises, then we can conclude that that came from the effect of a gravitational wave passing by. So this is so we need, that's why they have put these detectors in some desert, so that we reduce the seismic noise. And it's a major challenge, and therefore they want to put the detector in the space, which is called LISA, might be up in the next 15 years. So in space we would not have seismic noise, and much more better detectability for that reason. And we can also make the arms very long, because on Earth, if we go beyond, so these arms are 4 kilometers long. So if you go beyond 4 kilometers, the Earth starts to curve. In space, we won't have that problem. So yeah.
Do the gravitational waves move out in a spherical pattern from the black holes, or is it something, or does the orientation have an effect on?
So the emission would not be exactly spherical. It would depend on the masses of the system. So if the masses are non-symmetric, so let's say one is 30 solar mass and the other is 5 solar mass, then the gravitational radiation would be channeled in one particular direction more than the other. But if they're equal masses, it might go spherically everywhere, if they're exactly equal.
So the ones we detect, it's a bit like exoplanets, if you're looking at the ones like on a particular angle, you get more that we don't see because of that.
Yeah.
Further to that, does the plane of the orbits affect the distribution of the radiation? Like, in other words, you get difference between the poles of the orbit, or the orbit before they merge, versus what comes out of the equator of the orbit?
It's a good question. I think if your angle is in the plane of the binary system, then you might expect a larger intensity. Although I'm not sure about that. But my guess is that it would be larger if you are within the plane, and less if you are orthogonal to it.
One other thing, with the vacuum energy they're talking about inside the gravastars or the black hole, are they saying that the vacuum energy outside is somehow cancelling out so that it wouldn't have any effect?
Right. So there's no vacuum energy outside. So their proposal is that it's just inside, nothing outside. Yeah.
So how would that work when we see like the Casimir effect and that sort of thing, which
Right. So the vacuum energy is, although it's a very good idea, it's not currently accepted as the source of dark energy.
That's why they,
Yeah. So it because it's 10 to the 120 times larger, right? Yeah.
The fields are cancelling out somehow.
But that 10 to the 1 to the 20, that's quite an old calculation, is it, like 30 odd years?
Yeah, that's from 19.
Has that been refined since then?
So the calculation came from theoretical assumptions in quantum field theory, and the theory itself has not been refined since then. So it took its final form in the, when I say quantum field theory, I mean the standard model physics. It took its final form in 1970s, and no changes had been made since then. So the calculation has not been improved, and I think the purpose was just to showcase that it's way off from what we expect.
No, right away that it wasn't going to be anywhere near the result they did anyway.
So, do they, the people that support this idea, do they give any mechanism for how this coupling between the size of the universe and the mass of the black holes works?
So they don't give any mechanism. What they say is that black holes, at least the solution that we have, the Schwarzschild and the Kerr solution, are when these are, so a Schwarzschild black hole does not really have anything close to it. It's just one black hole living in an empty universe. And same is for the case of a Kerr. It's just one black hole living in an empty universe. So they say when you put these systems in a real universe, the boundary conditions change. And therefore the solution cannot be considered valid anymore. And so therefore they're free to make other hypotheses. Although when they make this claim about cosmological coupling, they do some calculation there. But in their calculation, so it has been pointed out that they might have missed or overlooked certain aspects. So in their equations, while they're solving it, they made an assumption which should not have been made from the beginning, but it should follow from you solving the equation. So because they make an assumption early on, which might not have been true, that then influences their further results. But this is a hypothesis, which so the Gravistar bit is their hypothesis. It's not supported by their work.
Anything online, Steve?
No, I don't think so.
Okay, if there are no more questions, I'd like to thank Sohan for coming up, giving us this really interesting talk. So thanks very much.